Today we are going to start on chapter 8 of the book. Um, I'm going to have 3 lectures in all for covering chapter 8. In the first lecture, we're going to talk about interacting systems, introduce the concept of having not just one but many objects, and look at how the forces in between these objects interact with each other, these systems interact with each other. In lecture 2, I'm going to cover pulleys and strings, and finally in the last lecture I'll go through detailed examples on the topics that we will be covering in chapter 8. Chapter 8 basically covers Newton's third law, which states that for every action there is an equal and opposite reaction, which I'm sure most of you have come across sometime in your lives before, whether in high school or some other introductory physics course. Now, I must warn you that chapter 8, when you read through it, it seems a rather simple chapter, but I've found that students have some difficulty in doing problems in chapter 8. There's some conceptual barriers that one needs to overcome. So chapter 8 is deceivingly simple in a sense. That's why I decided to allocate three lectures to go through it. Now let us talk about this action-reaction pair. If we have two objects, here we have object A and object B, the two blocks which are in contact with each other, and as we have discussed previously, whenever two objects are in contact, we have normal force set up in between them. So here we have force of A on B, so this is our contact plane, so there is a vector to the right. Now that's a force that A exerts on B, and the vector pointing to the left is a force that B exerts on A. The notation that the book uses, let's say we're trying to show force, the first subscript is shows the agent, okay, and the second subscript shows the object. So FAB is the force that A exerts on B, as shown down here, and the FBA is the force that B exerts on A. It is very important that you abide by this convention that the book uses, the notation that the book uses, in order not to confuse forces. Now, up till now, we've had one object which we call our system, and then of course anything around it was termed the environment, and we had forces F1, F2, F3 acting on the system. Now, in chapter 8 we're going to have a number of systems. So we can have system 1, system 2, system 3. These are the different objects, and of course there are forces acting on each system. So let's say that there's F21. This F21 means it's a force that system 2 is exerting on system 1. By the same token, that means there's a force F12. That's a force that system 1 is now exerting on system 2, which is equal in magnitude but opposite in sign to it. Similarly, F23, that's a force that system 2 is exerting on system 3, and F32 is the action-reaction pair for the two F23, etc. And our analysis is going to essentially follow this principle that when you have a number of interacting systems, then we need to be able to identify for each force a reaction pair, so a pair that such that the force and its pair forms an action-reaction pair. Now, this exercise may get a little bit cumbersome, so we may not necessarily care about, for example, F13 or F32 in doing our analysis. For example, if system 1 was a man and system 2 was a desk, and we're talking about a man pushing a desk across the floor, so system 3 here would be sort of the earth. Okay, so the man and the desk, well, these are the two objects that are, let's say, moving, so these are the objects of interest for us. The earth is just stationary, sitting there, so we may not necessarily care about the force that the man is exerting on the earth. That we would not care about. However, the force that the earth exerts on the man, which we call the weight, that we do care about. So you need to be judicious in deciding which forces to bring into consideration and which ones to call simply external forces. So in the example before, our system 1 is the man, system 2 is the desk. Any force in between the man and the desk, any force in between the man and the desk, well, you need to be able to come up with the action-reaction pair, because that's our interactive forces between the two systems. But any other force is simply the external force from the environment. So this would be the weight of the desk, this would be the weight of the man, for example. And we don't really need to consider any other forces. So forces of interest, forces that are going to help us understand the problem, are those fall into two categories. The ones that form the action-reaction pair, these are the forces in between the two systems of interest. And the second category are all the external forces, the ones that act on either system, but we don't necessarily have to have an action-reaction pair identified for. Okay, so here is our man, in this case pushing a block, and if we were to show all the forces that exist in this picture, well, I'll put this picture up and let you kind of study it for a second. You may want to pause the video so that you can convince yourselves that all the forces that ought to be there are there. And this is this picture basically shows all the forces acting on the person, all the forces acting on the crate, all the forces acting on the surface and the earth. And all the action-reaction pairs are joined together by the dotted lines. So if the man is pushing the crate with FPC, that's this force right there, then that means the crate is pushing on the man with a force FCP, which is equal in magnitude but opposite in sign. It's pointing 180 degrees the other direction. And this dotted line indicates the fact that these two are an action-reaction pair. Similarly, we have the weight of the man, so that's the force that the earth exerts on the person, and by same virtue we have a force that the person is now exerting on the earth. So these two forces are now an action-reaction pair. If the magnitude of the force that the man exerts on the earth is exactly the same amount as the force that the earth exerts on the man. However, our person here having much less mass than the Earth, the person of course accelerates heck of a lot greater than the Earth does towards each other. So but again, in this analysis, I'm sure you'll realize that we don't really need to consider the force that the person exerts on the Earth, nor do we need to consider the force that the crate exerts on the Earth, but we do care about the force that the Earth exerts on the crate and the force that the Earth exerts on the person, etc. So when you do your free body diagram, you need to do your free body diagram. This is our person free body diagram. This is the free body diagram for the crate. You need to do the free body diagram for each individual system. So if you have 4 systems, then you need 4 free body diagrams. And on the free body diagram, do go ahead and show the forces acting on that system only. For example, in the case of the person, we have weight of a person, we have the normal force on the person, we have force of crate on the person, that's this force back here, okay, and this is propulsion force on the person. I'm going to come to this force in just a second, so let's just put this in our back pocket for the time being. And in the case of the crate, we have the force of the weight, of course, of the crate, normal force. There is static, well, there is a friction force from the surface on the crate, which is opposing the motion. The motion in this case we know is to the right. And of course the force that the person is pushing the crate by. And these two forces, of course, form an action-reaction pair, and typically what one does in solving these problems is you for example the values for the crate are given, these forces for the crate are given, so you would identify what FPC is. Having identified FPC, then you would need to plug that here to find, for example, what the propulsion force on the on the person would be. Without knowing this, of course, you could not have figured this out because there are too many unknowns. So you figure out one of your unknowns from one free body diagram of a second system, for example, and then use that value in the free body diagram of this first system to figure out what the problem is after. Now, what is this propulsion force? Well, propulsion force is the force of the surface on the person. When the person pushes on the surface, you see this force right here, the one I'm showing in green, this is FPS. That's the force that the person is exerting on the surface. That's how we walk. We push the ground backwards. And if we don't have a slippery shoes, then as we push the ground backwards, what happens due to static friction between the sole of our shoe and the ground pushes the person forward. The ground pushes us forward. That's called the propulsion force. So FSP and FPS, these are an action-reaction pair. So FSP, that's the force of the surface on the person, exists as an action-reaction pair with FPS. FPS is the force that the person pushes the ground backwards by, and FSP is the force that the ground pushes the person forward. Now, this phrase action-reaction pair may imply that one force comes before the other, and in fact these action-reaction pairs, they either exist simultaneously or they don't exist at all. So don't think that one leads to another. That's not the case. They either exist together or they don't. Now, I think I have examples of propulsion force here. So, in propulsion force, the person pushes backwards against the earth pushes the person forward, and it's all due to the static friction between our feet and the ground. So the force to the left is the force that the person exists on the surface, and the force to the right is the force that the surface exerts on the person, or the propulsion force. A car moves forward by the same token. The wheels push the road back. That's this vector right there. So that's the force of car on road. And this is force of road on car, which is pushing the car forward. That's how a car moves forward. The propulsion force. Now, in the case of thrust force, F thrust, that we encountered in previous chapters, nothing pushes against something. The rocket moves forward because gases are pushed out of the rocket. So the gases that are inside the rocket are fired up and pushed out, and when we study conservation of momentum in the next chapter, we'll understand why an object moves forward as a result of this this action. So F thrust is different in nature to the propulsion force of a person and a car. Now, both person and a car, they have internal engines. So for a propulsion force to exist, you need to have an internal engine. Our internal engine, of course, is the chemical activity that goes on inside our body, and of course the car's internal engine is the engine that's inside the car. So a book doesn't have an internal engine, so a book cannot have propulsive force. So you need to have an internal engine if you're talking about a propulsion force. So just please do remember that it's the static friction between the surface and the object, whether it's our feet or the tires of a car, that lead to propulsion force. If static friction coefficient is 0, then no matter how hard we push against the ground or how hard we spin the wheels of a car, then we would not move forward. So now let's consider the scenario of a car being towed by a truck. Let us decide on our objects. Well, object number 1, of course, is the truck. Object number 2 is the rope. Object number 3 is the car. These are the systems of interest. Of course, we also have the earth and the surface of the road as other systems, but because earth and the surface of the road are stationary in this case, we're not really interested in analyzing their motion, so we can treat them as the environment and really look at the truck and the rope and the car as the three interacting systems. So here's a free body diagram for the truck, free body diagram for the rope, and free body diagram for the car. So what are the forces acting on each system? Well, in the case of the car, of course, we have the weight of the car, it's W car, normal force from the ground on the car. There is some friction force from the road on the car. Motion is to the right, V, alright. And the tension of the rope on the car, so that's the tension in the forward direction, like this. So that's the tension of the rope on the car, TRC. If you then look at the rope, let me use green in this case. Well, there is the force of the car on the rope, so there's a force of the force of the car on the rope, and there is also force of the truck on the rope, which is this way. So force of the truck on the rope. And if you take a look at, let me change the color to black in this case. For the truck, we have the first obvious one, of course, is the force of the rope on the truck. So there's a like this. So this is the force of T truck on the rope, and then we have weight of the truck. This is W truck, normal force on the truck, and the propulsion force that the truck has. So if it's a rear wheel drive, then this is F truck. That's the propulsion force on the truck, and in this case I'm ignoring any rolling friction that the truck may have with respect to road. Had we not ignored it, then there would be a small friction force, rolling friction, that the truck will have. There will that the surface will exert on the truck, but let's just ignore it for this example. And the free body diagrams are shown below here, and from these three free body diagrams, it's easy to identify the action-reaction pairs, mainly the force of the rope on the car and the force of the car on the rope. Similarly, the force of the truck on the rope and the force of the rope on the truck. So these are our two action-reaction pairs, and you would then go about solving the problem. This example is from the book, so please do refer to the chapter to see the algebra behind solving whatever it is that the example was asking for. But what I wanted to illustrate here is how you go about constructing the free body diagram. So we have one free body diagram for each system. You identify, as we've done before, you identify all the forces acting on the system. So you identify the forces acting on each system. Write those forces down on your free body diagrams. Identify your action-reaction pairs, and then apply your Newton's equations to each free body diagram. Find the unknowns and solve for whatever it is the problem is after. So in short, Newton's third law says that for every force occurs as a member of an action-reaction pair. Well, that's easy to remember. What is difficult, well, what's easy to forget in the early days is that these action-reaction pairs always act on different bodies. So please do pay attention to it. You cannot have an action-reaction pair on the same free body diagram. The action-reaction pair forces always occur on different free body diagrams. If you have a free body diagram with a couple of forces and you identify these two forces action-reaction pair, that's a big no. So action-reaction pairs always occur on different objects. That's your sanity check. It sounds simple, but trust me, when you work through problems, it's very easy to fall into this trap. This is the most difficult thing that students find in remembering, and that action-reaction pairs are always opposite in direction. That's conceptually simple to accept, and that they're equal in magnitude. So this is a slightly more difficult concept to appreciate. In fact, Newton hypothesized this point, which later on went to proving by demonstrating that his laws were universally obeyed by small and large objects. So their action-reaction pairs are always equal in magnitude but opposite in direction. So if we were to take a look at this scenario here, where we have two blocks, block A and B, where block B is has a greater mass than block A, and we apply a force by our hand to the right, and we cause the two blocks to accelerate to the right, and we're talking about the frictionless surface. How do we go about it? We have an interacting system, so we have our hand, object A, object 2, or hand system, hand system A, system B. So we need to consider three free body diagrams here, one for hand, one for A, one for B. And if you only consider the forces acting along the x direction, to simplify the analysis a bit, what do we have? Well, first of all, hand is in touch with block A, which means that there's a contact force from A on hand, and this vector right there is to the left. There is no other force in the x direction on A, on hand rather. Now when you consider object A, well, there's a force of hand on A, so this is F hand on A, which is our vector to the right, and because the object A is in contact with object B, there is a normal force from B acting on A, and that's this fella right there. Okay, and for object B, well, there's only, it's in the x direction, there's only a force of A on B, which is acting on it in the x direction. No other force in the x direction is acting on B. Now Newton's third law says that FBA and FAB form an action-reaction pair, and FAH and FHA form an action-reaction pair. Okay, so if you look at these free body diagrams, you see that the net force on A is this little vector there, and the net force on B is this larger vector shown in the right here. And sure enough, this makes sense because we know the objects are accelerating to the right with acceleration A. In this case, both accelerations must be the same. The objects don't lose contact, they kind of get accelerated to the right equally. And since mass of A is smaller than mass of B, then F net A divided by mass A is equal to F net B divided by mass B, and they're both equal to magnitude of A, of course. So you see that to accelerate a larger mass by the same amount A, well, I'm sorry, larger mass by the same amount A, you need a larger net force to the right. That's why F net B in this case is a larger force than F net A down here. Now in this example that we just did, I said that obviously the two accelerations are equal in magnitude. Well, this is something that you need to do in majority of the problems for this chapter, and that's identifying acceleration constraints. What we mean by acceleration constraints is if you have interacting systems, so system 1, system 2, system 3, and they are kind of moving somehow together, then you need to be able to identify when these systems have equal magnitude accelerations. Identifying interacting systems that have equal magnitude accelerations is called acceleration constraint. In the case of our car being towed by a truck, if the rope is under tension or is inextensible, so there's no stretching of the rope, then acceleration of the car and acceleration of the truck are equal in magnitude, and in this case equal in direction as well, of course. So that's identifying an acceleration constraint for our system. Don't assume that the acceleration are equal to start with. Write each acceleration for each object with its own identifying subscript, and then apply the acceleration constraint law and go ahead and say that because the objects are moving together, they're attached by a rope, a rod, super glue, whatever it is, then the two accelerations must be the same, i.e. we can just omit the subscripts. In the case of an object being pulled down, which is sitting on table A, on the table, that's object A, is connected to mass B, let's say friction is 0 to make things simple. Of course, object B accelerates downwards due to weight B by acceleration AB, and because object B is connected via a rope to object A, then object A accelerates to the right with acceleration A. And in this case, our acceleration constraint says that the magnitude of the two accelerations must be the same, okay, because we have they're connected to each other. However, note that the directions are not the same. In fact, if you go okay, let's continue from where we left off before the bells rang here. My apologies for that. Anyway, I was talking about the acceleration constraint with regard to these two items, object A and object B. The magnitude of each acceleration is the same. However, note that if we choose our y-axis pointing upwards, of course acceleration B is equal to minus A, if we say that this is equal to A. And if this is our x direction, then acceleration of object A is equal to plus A. So AB and AA and AB may have the same magnitude, but they're opposite in sign in this particular case. So identifying these acceleration constraints is the main part of problem solving in this chapter. Now this is another example from the book. What we have is a crate at the back of a truck, and we are given the mass of the truck, mass of the crate, and the coefficient of static friction between the crate and the flatbed of the truck. And we are asked to find what is the maximum propulsion force on the truck such that the crate doesn't slip from the back of the truck. And to do that, so here in our picture here we have we've shown the propulsion force. That's what we're trying to figure out. And of course AC and AT are the acceleration of the crate and the truck respectively. Now let me jump immediately to our acceleration constraint here. Down here I'm circling that in red. So AC is equal to AT, and so we can just go ahead and call that A. So that's how we identified our acceleration constraint in this particular problem. Next, let's go ahead and do the free body diagram for both the truck and the crate. So this is the free body diagram for the crate, this is free body diagram for the truck. For the truck, actually let's do the one for the crate first. We have the weight of the crate, W crate, normal force from the truck on the crate, and of course the static friction force, F truck on crate. That's the force that accelerates the crate to the right. And here's the free body diagram for our crate. We have weight of the crate, normal force of truck on crate, and the static friction force, or the force of the truck on crate. Now as far as the free body diagram for the truck is concerned, of course we have the weight of the truck, Then we have the normal force of the road on the truck, right? And the crate is in contact with the truck, therefore there is a normal force from the crate on the truck. These are the forces that are typically left out in the early days when you attempt problems in this chapter. So don't forget the normal force of crate on truck, and it's pointing downwards. Recall that if two objects are in contact, this is object 1, object 2, normal force exists at the plane of contact, and it always points towards the object. So this is the normal force due to object 1 acting on object 2, and this force pointing upwards is the normal force due to object 1 acting on object 1 normal force due to object 2 acting on object 1. So the normal force of crate on truck points downwards, of course. And of course we have the force of crate on truck, the static friction force of crate on truck, which is pointing to the left. And Newton's third law says that these two forces here form an action-reaction pair. So do these two right there, normal force of truck on crate and normal force of crate on truck, form our second action-reaction pair. So then you go about doing your analysis. You do the analysis in the XY direction for our crate. You also do the analysis in the XY direction for our truck. These are using our Newton's equation. Sum of the forces equals mass times acceleration. And from the equations for the crate, these are the equations in black, you can show yourselves that you'll end up with an expression like this for the force of truck on crate. And the top equation I've marked as equation 1. This is this equation right here. So we'll keep this in our back pocket. In fact, let me back up and say that the question is after maximum propulsion force. So maximum propulsion force would mean that we have maximum A, maximum acceleration, and maximum A happens when the static friction force between the truck and the crate is maximum. So at Fs max, at maximum static friction force, we have maximum propulsion force on truck, and that's what the problem is after. So you need to make this connection that the problem is after maximum propulsion force, but that really means that we need to find out maximum static friction force that we can exert on the crate without it slipping. So that's this equation right there, this expression right there, which I've called equation 1. Now from the Newton's analysis on equation on the free body diagram for the truck, we end up with the blue expressions here, and I've marked equation 2 as you can see, and from equation 1 we can come up with an expression for acceleration in terms of the known values mu s and g, and from equation 2 from up there we can then calculate we can then come up with an expression for Ft max, which is shown here. And mt, mc, mu s and g are all knowns, so we can go ahead and calculate what the problem was after. So I'll leave it to you to work through the algebra and show yourselves that I haven't made any silly mistakes here. So just to recap, please do remember that if you have interacting systems, then forces always occur in pairs. So there's a force of A on B, and this is a force of B on A, for example. Actually, the way I drew it is wrong, so let me change the force of A on B is here. There's a B on A is on this side. I think that's how I had it before anyhow. And that the action-reaction pairs have the same magnitude but are of course opposite in direction. One thing, if you have the Earth and we have an object here with mass m, as you know, the Earth exerts a force which we call a weight of the object, so that's the force of Earth on mass. Similarly, our mass exerts a force on Earth which has the same magnitude but is opposite in direction. Now the two objects, as a result of these forces, accelerate towards each other, but as I said, since mass of the Earth is much greater than the mass of our object here, so let's call it mass of the object, then the acceleration that the Earth experiences as a result of this force WME is much less than the acceleration that acceleration that the Earth experiences is much less than the acceleration that acceleration of the object experiences. So like it's negligible. So just wanted to point this out. We're going to cover this concept in more detail in chapter 12 when we do Newton's gravitational theory. So let me stop this lecture here. In the next lecture I'm going to cover ropes and pulleys, and then the final lecture we'll work through some examples.